Hello, everyone. I'm Yoshihiko Suzuki from Osaka Prefecture University, Japan. The title of my presentation is on Koopman operator framework for semi-explicit differential algebraic equations. This is the outline of my presentation. My work is on analysis of nonlinear dynamical systems described by semi-explicit nonlinear DAEs. This system is a coupled system of differential equation and algebraic equations. First of all, I'd like to introduce motivation, purpose, and content of my presentation. Here I have two research targets, nonlinear DAEs and Koopman operators. In the DAE models, X is called differential variables and Y is called the algebraic variables. Also, F and G are nonlinear and smooth functions. This DAE model has been widely used in practice, such as power networks. In this presentation for the systems described by nonlinear DAEs, we consider so-called Koopman operators. For this, we use so-called flows, that is a nonlinear map from the finite dimensional state space M to itself. Then the Koopman operator UT is defined as a composition operator of nonlinear flow with observable F. This observable F is a scalar valued function defined on the state space. An important fact that this flow is nonlinear. On the other hand, UT is linear. This operator is defined on the space of observable, such as that is a function space. Using this Koopman operator on function space, it is possible to consider analysis, control, and design of nonlinear systems. This is called the Koopman operator framework. For the detail of this framework, please see my recent book in the left. Regarding this presentation, the existing theories of Koopman operators have been limited to mainly ODEs, such as ordinary differential equations, and PDEs, so the partial differential equations. In this presentation, I tried to develop the theory of Koopman operator for systems described by semi-explicit nonlinear DAEs. In particular, I'll focus on the spectrum of the Koopman operator for systems with stable equilibrium points, EPs. Such stable dynamics are regarded as a regular behavior described by the DAE. In particular, I'll develop so-called Koopman mode decomposition, that is expansions of the time evolutions X of t and Y of t in terms of the spectrum of the Koopman operators. This is a natural extension of the ODE case developed by Professor Igor Mezic in 2013. Here is a key idea of my theories. This is a transformation of DAE into ODE. For the algebraic equation capital G's, we can introduce the transformation phi of x from the differential variable x to the algebraic variable y. By using this, it is possible to transform the DAE into the pure ODE systems. Here, the existence of this transformation phi of x is guaranteed by the so-called implicit function theorems. For this, we need to assume the existence of the inverse of Jacobian matrix, capital G, with respect to y. Under this assumption, we district our attention on the region Earth, and the dynamics evolve on the Earth. For these regions, the stability of the equilibrium point of DAE, denoted by x aster and y aster, can be evaluated with eigenvalues of the Jacobian matrix, capital F, with respect to x and transformations. Below, we use the notation lambda1 to lambda n to represent the linear eigenvalues with number n. Based on these preliminaries, we can introduce the definitions of Koopman operator for DAEs. Let us consider the D-geometry attraction of stable equilibrium point X asta and Y asta denoted by capital A. Then it is possible to introduce so-called semi-flow capital ST that is a nonlinear map from A to itself. Also, to consider the Koopman operators, we introduce so-called observable F defined on D-geometry attractions. Also, we assume that this F is continuous on A. Then the Koopman operator capital UT is defined as a composition operator with observable F and nonlinear flow ST. In this, the Koopman operator U is parameterized by time t that is non-negative. So this one parameter family of the Koopman operators form a semigroup. Here, the interesting observation from these definitions that the transformation phi of X is also observable defined on the capital A. So by definition, the actions of Koopman operator UT to the transformation phi I describes of the time evolution of algebraic variable y of t, like this. Okay, here is the main result of spectral of the Koopman operator for DAE. We now assume the nonlinear function capital F and capital G are real analytics. And also the space of observable capital F is also the space of all real analytic functions on the region of attraction capital A. Then the spectral characterizations of X, that is a differential variable, the spectral characterization, the time evolution X of t is represented as follows. This formula is relatively complicated. Here, I'd like to emphasize on 2 points. The first point is that this formula holds for all initial conditions X of 0 from the entire region of attraction capital A. So this result is a semi-global result beyond the neighborhood of the stable equilibrium point. The second one is that from these characterizations, the spectrum of the Koopman operator UT consists of the point only. This point spectrum of the Koopman operator denoted by lambda is defined as here with associated eigenfunction phi lambda. This Koopman eigenfunction phi lambda is also observable defined on capital A. This is the last content of my presentation. As a corollaries of the spectral theorems, it is possible to derive the spectral characterization of the time evolution of algebraic variable y of t, like here. In the right-hand side, the second term is for the expansion in terms of Koopman eigenvalues, lambda j, that the same as the linear eigenvalues. Also, the third terms, the Koopman eigenvalues of the linear combinations of the linear eigenvalue appeared here. This third terms is clearly due to the nonlinearities of the vector fields capital F and the nonlinear function capital G. An important implication from this is that by using this expansion of y of t's, it is possible to estimate the Koopman eigenvalues directly from the time series of algebraic variable y. This is very useful in applications to power systems because in the power networks, the variable x is not easy for direct measurement. On the other hand, the variable y is easy for direct measurement based on the phasor measurement technologies. So this is the summary of my presentation. I provided the spectral theory of the Koopman operator for the systems described by the nonlinear DAEs. This theory is regarded as a part of the Koopman operator theory for ODEs defined on analytic manifolds. As a future work, it is very important to work on specific nature of DAEs in the framework of Koopman operator to cause irregular behavior such as jump behavior. Also, it is important to apply this theory to power networks. That's all I have. Thank you for your kind attention.